welcome back my AP Calculus champions. In this problem we're going to be talking about seawater. So this problem says the depth of seawater at a location can be modeled by the function h that satisfies the differential equation, this function here, where h of t is measured in feet and t is measured in hours after noon, where noon is t equals 0. It is known that h of 0 is equal to 4. Problem A says a portion of the slope field for the differential equation is provided. Sketch the solution curve y equals h of t through the point 0, 4. The slope field, it gives you an idea of what the slope of the function is at various points throughout this graph. So one thing you really want to make sure is that you're actually sketching the curve through that point. So we have it here. So make sure that that's your starting point for your solution curve. So we're just basically going to be, tracking along, making sure that the slope of our function, of our curve, matches what the slope field looks like. So something like this, okay? Roughly, more or less. And that is pretty much it for problem A. So let's move on to problem B. So this one says, for t is between 0 and 5, it can be shown that h of t is greater than 1. Find the value of t for t is between 0 and 5, exclusive at which h has a critical point. Determine whether the critical point corresponds to a relative minimum, relative maximum, or neither a relative minimum nor a relative maximum of the depth of seawater at the location. Justify your answer. Okay, so a critical point. What is a critical point? When does that occur? So one easy way for me to remember this is, so it's talking about minimums and maximums. So, this would be a critical point, and this would be a critical point as well. And what do these two things have in common? This is when the slope of the curve is equal to 0, or when it is undefined. So our critical points are going to happen when dh over dt, the derivative of h of t, is equal to 0 or undefined. So we want to find the point between t equals 0 and t equals 5 at which this happens. So let's go ahead and set our dh of dt equal to 0 or undefined and see what we can figure out here. So our dh over dt is 1/2 h minus 1 times cosine of t over 2. We want to set that equal to 0. So it's not actually going to be undefined at any point here. So we kind of don't really need to include this part of the definition of a critical point. But let's say, for example, we had like t minus 1. Let's say our dh over dt looked something like this. Then we would say that actually, if, when t is equal to 1, our dh over dt is going to be undefined because we're going to be dividing by 0. But that's not the case in our example. So we can go ahead and just set equal to when it's 0. So let's think about this for a little bit. So we kind of have two parts to this equation. We have our 1/2 h minus 1, and then we have our cosine of t divided by 2. And if either one of these is equal to 0, that's going to set the entire function equal to 0, right? So when are these two equal to 0? Let's take a look at them step by step. So 1/2 h minus 1 is equal to 0. So we can multiply both sides by 2. So now we have h minus 1 is equal to 0. 0 times 2 is going to be 0. So is it ever going to be true that h minus 1 is equal to 0? Well, no, because remember it said here that between these points, h of t is always going to be greater than 1. So this would only ever happen when h is 1. But since it's going to be greater than 1, we're never going to actually hit 0 here. So we actually need to figure out when cosine of t over 2 is going to be equal to 0. So it kind of helps if we graph what our cosine looks like. So remember, cosine starts at 1 at 0. Cosine of 0 is 1. Then we go down like that, and then we do something like this. So at what point are we intersecting our x-axis? At what point is cosine of x equal to 0? Well, this happens at pi over 2, and then it also happens at 3 pi over 2. So for setting cosine of t over 2 equal to 0, So we know that cosine of pi over 2 is equal to 0. We know that cosine of 3 pi over 2 is equal to 0 as well. So what are the two values that we found so far? They're going to be when t is equal to pi and when t is equal to 3 pi. Wait, hold on a second. Didn't we say that t has to be between 0 and 5? Yeah, so pi is actually between 0 and 5. Pi is like 3.1415, blah, blah, blah. That's between 0 and 5. 3 pi, on the other hand, is going to be 3 times 3.1415, blah, blah, blah. And that is actually no longer less than 5. So this is not a candidate for our critical point. So it looks like we've found it when t is equal to pi. This is one of the answers that they're looking for. When t is equal to pi, there is a critical point. Now we need to figure out whether this is a relative minimum, a relative maximum, or neither. So let's go ahead and do that now. So as we said before, here's what a relative maximum looks like. Here's what a relative minimum looks like. What can we say about the slopes here? So we can see here the slope is positive. Then once we hit that critical point, that relative maximum, our slope now becomes negative. So there's a change in the slopes. Our relative minimum, so we start off with a negative slope, we hit the relative minimum, now our slope is positive. We're basically looking for if it's going to match either one of these conditions. So let's go ahead and test this out. So we need to know what the slope is on either end of our critical point. So we know the critical point is at t equals pi. So between 0 and pi, we need to figure out what's happening with the slope there. And then also between pi and 5, we need to figure out what's happening with that slope. Okay, so let's look back to our slope function. What does it look like? Let me just bring it down here. Here's our slope function. So between 0 and pi, what does our slope look like? So we have our 1/2 h minus 1 times cosine of t divided by 2. We know that this is always going to be greater than 0. And why do we know that? Once again, going back to what we set up here, h of t is going to be greater than 1. So we know that this will never be negative. So we know that this part is always going to be greater than 0. It's always going to be positive. Okay? What about cosine of t divided by 2? Between 0 and pi, what are its values going to be? Well, if we refer back to our graph of cosine, so we're looking at the values between cosine of 0 and cosine of pi over 2. So what are the values here? Remember, here are the two values we're looking at, and it looks like all of these values are going to be positive as well. So a positive times a positive means that our slope is positive for t is between 0 and pi. Okay, how about between pi and 5? So once again, 1/2 h minus 1. As we established, this is always going to be positive. So now we need to look at what's happening to the sign of cosine of t over 2. So we're looking at the values from cosine of pi over 2 and cosine of 5 over 2. So cosine of pi over 2, cosine of pi over 2 is here, 5 over 2, I'm not actually sure where that is here, but we know that 3 of pi over 2 is going to be greater than 5 over 2, so we know that each of these values are negative here, so this sign is going to be negative. So we know that the slope is negative for t is between pi and 5. We found out that on the left side of our critical point, the slope is positive, and then on the right side of our critical point, our slope is negative. So which of these two cases does that match, if it does match one? It looks like it matches this case, okay, where we're approaching that critical point with a positive slope, and then after we hit the critical point, it's a negative slope. So we would say that at t equals pi, there is a relative maximum because for t is between 0 and pi, dh over dt is greater than 0, and for t t is between pi and 5, dh over dt is less than 0. And that should be the answer for part B. Moving on to part C. This one says, use separation of variables to find y of h of t, the particular solution to the differential function, the dh or dt we've been dealing with the initial condition h of 0 is equal to 4. All right, separation of variables. What are we doing here? So you might notice that on both sides of this equation, we have variables in terms of h and t. So, on the left we have dh and dt, and then on the right we have h and we have t. So with separation of variables, we want it to look separated, okay? We want our h's on one side, our h terms on one side, and our t terms on the other side, so that we can put it in this format. So let's go ahead and start doing that. So we start off with dh over dt is equal to 1/2 h minus 1 cosine of t divided by 2. So we can multiply both sides by dt. So now we have dh is equal to 1/2 h minus 1 cosine of t over 2 dt. And then let's divide both sides by h minus 1. So now we can divide both sides by h over 1. So dh divided by h over 1 is equal to 1/2 cosine of t over 2 dt. Now we have it in terms of just t and dt on one side and dh and h on the other side. So we actually want to get rid of our dt and our dh's, because what we want the function to be in terms of is just h and t. So we can go ahead and integrate both sides. So take the integral here and the integral here. This is, on the left side, we have one of those special cases that you just have to memorize. Remember, this is a non-calculator problem, so you just have to recognize that this is going to be ln of absolute value h minus 1. And then on our right, so when we're taking the integral of cosine, that is going to be sine of t over 2. And when we take the derivative of sine, multiply by the derivative of whatever's inside as well. So that's where we get our 1/2. So that all checks out on the right side. And then since we integrated, we need to have our constant of integration. It's looking a little more simplified. We don't have our dt's, we don't have our dh's, but we still have that constant of integration, and we still have it a little bit more complicated than just, h is equal to t terms. Actually, let's go ahead and solve for our constant of integration. So we were given this initial condition, h of 0 is equal to 4. So when t is equal to 0, h is 4. So we can go ahead and put that into this equation to solve for our c. So ln of 4 minus 1 is equal to sine of 0 divided by 2 plus c. What does the graph of sine look like? It starts at 0 when sine is 0, and then it does something like this. Luckily for us, we're solving for the value of sine when sine is 0, so it looks like that's just 0. So this actually just goes away. So we have ln of absolute value of 3 is equal to c. We don't need those absolute value bars, so we can just say ln of 3 is equal to c. So now we can go ahead and actually plug that into our function here. So it's a little bit more, it has fewer variables inside of it. So ln of h minus 1 is equal to sine of t divided by 2 plus ln of 3. All right, still a bit complicated on the left side. Let's go ahead and see what else we can do to simplify things. So we have an ln here. We want to get rid of it. The way we can get rid of it is taking both sides to the power of e. So take that to the power of e and this to the power of e. So these two should cancel out. So now we have absolute value of h minus 1 is equal to e to the sine of t divided by 2 plus ln of 3. One of the cool things about powers is that you can go ahead and drop this ln 3 if you rewrite it like this, e to the sine of t divided by 2 times e to the ln of 3. That's the same thing. And now we can go ahead and simplify this some more. So these two cancel out. So we get that h minus 1 is equal to e sine of t divided by 2 times 3. So we can just pop that 3 out front there. So now we still have these absolute value bars, and we want to go ahead and get rid of them. So how do we get rid of them? Well, we know that we can set h minus 1 equal to plus or minus 3e to the sine of t divided by 2. This is the same thing as what we were looking at in the previous line. But now let's figure out actually if it's going to be a plus or a minus. This is going to be one of the two. So what do we know? We know that in the original problem statement it said for t is between 0 and 5, h of t is going to be greater than 1. So we know for that interval, h of t is going to be greater than 1. So what does this mean? This means that this side is never going to be negative. It's always going to be greater than 0. We know that h is going to be greater than 1, so it'll never be negative, basically. So when we're picking between the positive or the negative, we know that it's going to be strictly positive, okay? So we can just get rid of that sign. It's just positive up front. So now things are a lot more simplified. Now we just have one more step, and then we finally have it in terms of h on one side and all the t and other stuff on the other side. So add 1 to both sides. We have h is equal to 3e to the sine t divided by 2 plus 1. And this is our final answer for this problem. So hopefully this helps you out with these AP Calculus problems. If you have any questions, feel free to leave them down below and I'll get back to you. And I hope you have a great rest of your day.